Hello, and we're going to take a little bit of time here to have a look at limiting and excess reactants. So we have put together a set of questions that will help us review those topics as we head into the main part of our course. Obviously, limiting reactants in stoichiometry is a big deal when it comes to generally any quantitative chemistry. So the list of questions will sort of ramp up with the more difficult ones hopefully towards the end. And as we work through them, make sure that you get a chance to try the questions before you look at the answers or the worked solutions. And if you get stuck, obviously, just continue watching the video. So the first question is, define the terms limiting reactant and excess reactant. So we have the idea of a limiting reactant. And a limiting reactant is simply any chemical species that runs out during the chemical reaction. A limiting reactant controls how much product is produced, therefore it's limiting. So we're just going to write it is the reactant that limits the amount of product made. The next part is what is the excess reactant? And the excess reactant basically is all the other reactants that there is too much of. It doesn't really control the reaction at all. And normally the helpful thing is to use an excess reactant in chemistry so we can actually get all of the desired limiting reactant to react. So if we were trying to reduce all of the copper in a reduction reaction, we would probably put an excess reactant present to make sure all of the copper does react. And this is just going to write reactant left over at the end of a reaction. And there could be more than one if there's more than a couple things in the reaction side. So the next question says, why are the amounts of products formed in a reaction determined only by the amount of limiting reactant? So just for the future reference, we're going to call limiting reactants LR, and we'll use ER for excess reactant or reagent. Limiting reagent, excess reagent are also the same thing. When the limiting reactant runs out, so for example, if we had copper 2 nitrate plus aluminum metal, and we end up with aluminum nitrate plus copper solid, generally for our intents and purposes, we really want what we're trying to reduce, the copper nitrate in this case, to be the limiting reactant. So since that's the limiting reactant, we know the products will be controlled by that. We should probably balance this just for fun. But for every 3 moles of copper nitrate we use, if this is the limiting reactant, we can write limiting reactant right on it. We'll get 2 moles of this and 3 moles of copper. The excess reactant, which is usually the other compound, as we did in lab, we used aluminum foil to reduce copper. The aluminum was present in excess, hopefully not in too much. So when the limiting reactant runs out, reaction stops. The stoichiometry of the reaction is stoichiometry of the reaction is therefore completely controlled by the limiting reactant. I'm just going to continue to write LR for limiting reactant. Why should you base your choice about what compound is the limiting reactant on the number of moles, not the initial number of grams? Obviously, compounds have different masses, and we're talking about molecules. 3 molecules of copper nitrate and 2 molecules of aluminum. The copper nitrate is going to weigh a lot more, so it's going to take a lot more mass to make 3 molecules up or 3 moles up of this than it would for that. So it's really misleading. We have to remember that molar mass, we're talking about molecules, and molar mass just allows us to go from grams back to mass. So molar mass converts, well, obviously mass, but I'm going to write grams to moles, which reflect molecules, which is all that matters. So here's a little question. It is a limiting reactant question. However, it's obviously not dealing with chemistry. It says a bottling plant has 121,515 bottles, each with a capacity of 355 milliliters, 122,500 caps, and 40,875 liters of beverage. How many bottles can be filled and capped? So first thing, I have milliliters and liters, so I'm going to convert this to liters just by dividing by 1,000. So let's see if that many bottles filled with that much beverage is going to use up all of the solution. It is pretty evident that I have 121,000 bottles and 122,000 caps. So I can tell right off the bat that the caps are in excess because I'm going to have some left over. So I'm going to start with the bottles. I'm going to go 121,515 bottles times 0.355 liters of beverage per bottle. My unit of bottle will cancel out. So 121515 multiplied by 0.355 gives me 43,137.825 bottles, liters of beverage needed. I don't have that. I therefore know that I have more bottles than I can actually fill with that particular compound, with that idea. So I'm going to label the beverage, since I don't have that, since I am short beverage, it is the limiting reactant. So this is my limiting reactant. How much of each item is left over? Well, my beverage, which is my limiting reactant, will have none left over, so it'll be 0. And the limiting reactant will control how much of everything I use. So 40,875 liters times one bottle is 0.355 liters. Liters will cancel. Do a quick little calculation here. 4,875 divided by 0.355 is 115,140.85 bottles to be filled. I have 121,000 bottles. 515. Take away the 1,115 and 140. And we're going to, what we call, truncate this because the decimal doesn't really matter. We're not going to partially fill a bottle. It's 121,515. Take away 115,140. That's going to mean I'm going to have 6,375 bottles left over. So there's that. I got my beverage is 0. I know my no beverage left. I have 6,375 bottles left. And then finally I also have caps. So let's look at the caps. The relationship between caps and bottles is pretty straightforward. 1 cap per bottle. So I'm just going to take the 122,000 500 caps, and I'm going to subtract away the fact that I would need one for each bottle. Sorry, one for each bottle. I'm going to put the ones that we're actually going to use. To 122,515, take away. That's right. 122,500 caps. Take away 115,140 bottles. Gives me 7,360 caps. Will be left over. Which component limits production? It's the beverage. Which is probably good because that's probably the thing that's going to go bad. But that would make sense. So now we can look at an actual chemistry question. Sodium hydroxide reacts with carbon dioxide as follows. 2 moles of sodium hydroxide with 1 mole of carbon dioxide will give me 1 mole of sodium carbonate and liquid water. So it says, which reagent is the limiting reactant when 1.85 moles of sodium hydroxide and 1 mole of CO2 react? So what I do when I'm doing these questions, I usually cheat and look ahead at the next question. And question B wants to know how much sodium carbonate I'm going to make. So what I'm going to do is I'm going to use these moles, plug them into my balanced chemical equation, and figure out how much sodium carbonate I make. I'm basically going to be answering question B. However, I'm going to do it twice. And whichever starting material, the 1.85 or the 1, gives me the fewest number of moles of sodium carbonate, that will be my limiting reactant. So I'll answer A and B at the same time. So we'll start with sodium hydroxide, 1.85 moles of sodium hydroxide. It's already in moles, so if we're in grams, we have to go grams to mole to start. We're already in moles. So I'm going to do 1 mole of sodium carbonate for every 2 moles of NaOH, remembering that what we want to find we put on the bottom. And that means I'm going to get a 0.925 moles of Na2CO3. Okay, we'll do the exact same calculation, but we're going to do it with the other starting material, the amount of carbon dioxide. So 1.00 moles of CO2 times 1 mole Na2CO3 for every 1 mole of CO2. Units will cancel the moles, and that means I will produce 1 mole of carbon dioxide. Oh, well, it does mean that too, but 1 mole of sodium carbonate will be produced. So we compare them. Sodium hydroxide produced a fewer number of moles of product. So sodium hydroxide is my limiting reactant. It produced the fewer amounts of Na2CO3. And now I also have the part B answered in this one step. The part C says how many moles of excess reactant remain after the completion of the reaction. So 1.85 moles of NaOH. My excess reactant will be the other reactant, carbon dioxide. So 1 mole CO2 for every 2 moles of NaOH equals 0.925 moles of CO2 would be used. I start it with 1 mole. I am going to use 0.925 moles. And that's 0.075 moles of CO2 left. And that is a very, very basic stoichiometry question. It's a treat because it's already in moles, so you don't have to do the gram conversion as well. That just adds a step, but the process is exactly the same. So let's look at another one that's kind of like that. It says aluminum hydroxide reacts with sulfuric acid as follows. So I have a list of chemicals here: 2 moles of aluminum hydroxide, 3 moles of sulfuric acid producing aluminum sulfate, and 6 moles of water. So question A says which reagent is the limiting reactant when 0.5 moles of aluminum hydroxide and 0.5 moles of sulfuric acid are allowed to react. So you could do this visually. I need more sulfuric acid than aluminum hydroxide just because it's 3 to 2. So and since we have the same number of moles starting out, sulfuric acid will be the limiting reactant. Just for the sake of going through the steps, we'll do it just like we did above. Question B says how much aluminum sulfate will form. So that's what I'm going to find. I'm going to plug in each number. So 0.500 moles of aluminum hydroxide, and I get 1 mole of aluminum sulfate for every 2 moles of aluminum hydroxide. Gives me 0.250 moles of the aluminum sulfate. Do the same thing to the other reactant, 0.500 moles of H2SO4, 1 mole of aluminum sulfate, for every 3 moles, if you look at the coefficient of sulfuric acid. Zero point 167 moles of aluminum sulfate. So the aluminum sulfate, the sulfuric acid is going to produce less aluminum sulfate, so it's got to be the limiting reactant. So there's my limiting reactant, which is what we visually were able to determine to start. How many moles of aluminum sulfate were created? 0.167 moles. We did it above, so we're done with that. And how many moles of excess reactant remain under the completion of the reaction, or at the completion of the reaction? So we use our limiting reactant. Once you determine what the limiting reactant is, it's going to control everything for the rest of your reaction. My excess reactant would be the aluminum hydroxide. So 2 moles AlOH3 for every 3 moles of sulfuric acid. So 0.5 times 2 divided by 3 is 0.333 moles of aluminum hydroxide will be used. So that's what we're going to use. We have 0.5 moles. We're going to use 0.33 moles. Equals 0.167 moles of aluminum hydroxide left. And that question is done now. So question 5 is very similar to one of the ones we had on our pre-lab, so we can take a few minutes and make sure we really know how to do this. It'd be a great question to try ahead of time and then see how you do as we go over it. So when benzene reacts with bromine, bromobenzene is obtained, and there's the chemical reaction of that happening. What is the theoretical yield of bromobenzene in this reaction when 30 grams of benzene reacts with 65 grams of bromine? So theoretical yield is basically asking you to find the limiting reactant, determine how much of the product is formed, and go from there. So it wants us to determine bromobenzene, so that is this thing here. So the theoretical yield of bromobenzene would be, start with the benzene reaction, so 30 grams of benzene, C6H6. We got to go to moles. Benzene is 6 times 12 plus 6. I am just kind of giving you the rounded molar masses, but it's about 78 grams per mole for benzene. So I went from grams to moles, moles to moles. I have 1 moles of bromobenzene for every 1 mole of benzene. So question 7 says, when ethane reacts with chlorine gas, the main product is chloroethane, but other products can be produced containing chlorine, such as C2H4Cl2. The formation of these unwanted products reduces the yield of C2H5Cl. So we have an unbalanced chemical equation, which is known as a skeleton equation. we have, let's just check a quick balance of 2 carbons, 6 hydrogen, 6 hydrogen, 2 chlorine, 2 chlorine. So even though I'm calling it a skeleton, it is balanced. It says calculate the theoretical yield of chloroethane when 125 grams of ethane and 255 grams of chlorine are used. So looking ahead, I know that I need to figure out chloroethane later, so I might as well do it now. So 125 grams of C2H6 times 1 mole over, I need the molar mass of ethane, so that's 2 carbons is 24, plus 6 hydrogens is 30. My answers are not going to be crazy precise because I am approximating a lot of these formula weights. 1 mole to 1 mole. So 1 mole of C2H5Cl for every 1 mole of C2H6. And now we're going to go to the mass of chloroethane. So for chloroethane, I have 2 carbons, 5 hydrogens, and 1 chlorine is 64.45. So we just plug along, 125 grams divided by 30 grams per mole times 1 over 1 times 64.45 is 268.5 grams of chloroethane. So now we'll do the same thing for the other reactant, which is chlorine. 255 grams of chlorine One mole of chlorine is 70.9 grams. So remember, there's 2 chlorines in Cl2. 1 mole of Cl2, so 1 mole of C2H5Cl, 1 mole of chlorine times 64.45 grams per mole of the chloroethane. Let's see what we get. 255 divided by 70.9 times 64.45 is 231.8 grams. So that one's the smaller one amount, so chlorine must be your limiting reactant. So now it says calculate the percent yield. Percent yield is your actual, what you recovered, over your experimental, times 100%. So I got 206 grams. I should have got 231.8 grams, just pulling that number from here. About 90% or so. 206 divided by 231.8 is 88.9%. Ignoring significant figures here, but about 88.9% yield would be what that is. So number 8, we're starting to tie together some of the work that we've been looking at. It says the koala dines exclusively on eucalyptus leaves. Its digestive system detoxifies eucalyptus oil, a poison to other animals. The chief constituent of eucalyptus oil is a chemical called eucalyptol, which contains 77.87% carbon 11.76% hydrogen, and 10.37% oxygen. This is just a little bit of a review question, so we're going to, as we've always done, assume 100 grams. So that means I'd have 77.87 grams of carbon, 11.76 grams of hydrogen, and 10.37 grams of oxygen. So I have my three parts. Let's see if we can jam it all in this one line. So the first thing we do is we go to 1 mole. Do them all at the same time. So we're going to multiply them by 1 mole per however number of grams that is. So for carbon, that's 12 grams. For hydrogen, that's 1 gram. And for oxygen, it's 16 grams. So we'll do those calculations. 77.87 divided by 12 is 6.49 moles. 11.76 moles of hydrogen. 10.37 divided by 16 is 0.648 moles of oxygen. We have to normalize here, so we know one of them is present in the fewest amount, so we're going to divide by the one that has the fewest number of moles. 0.648, 0.648. So 0.648 divided by that is obviously equal to 1. 6.49 divided by 0.648 is approximately equal to 10. 11.76 divided by 0.648 is about 18. So we got our ratios. So I have C, H, and O. I have 10 carbons, 18 hydrogens, and 1 oxygen. And there is my empirical formula. So we get used to doing formula weights for our empirical formulas. So just to do a rough one, we have 10 carbons. So that's 120 grams. Just let's approximate them. So the formula weight is 154 grams per mole. Look at the actual values. I think we mean this is the molecular weight, but is 154 grams per mole. So since the formula weight is equal to the molecular weight, the molecular formula would be the same. There we go. A mixture of nitrogen and hydrogen reacts in a closed container to form ammonia. The reaction ceases before either reactant is totally consumed. At this stage, 3 moles of nitrogen, 3 moles of hydrogen, and 3 moles of ammonia are present. How many were present initially? So we need a balanced equation. We have nitrogen plus hydrogen giving NH3 ammonia. So if we put a 3 here and a 2 here, we have a balanced equation, technically called the Haber process. And realistically, it's a two-way reaction, but we're not to that part of our course yet. So we can do this out with our initial amount. So before we do anything, we don't know how much of this there has, but let's assume that there is no ammonia. The reaction ceased before anything happened. So we know after there were 3 moles of nitrogen, 3 moles of hydrogen, and 3 moles of ammonia present. So it's a little bit of detective work needed. And this is just, we can logic this out pretty easily. If we have an increase in 3 moles of ammonia, then we should be able to figure out what has happened. So, in other words, if I have 3 moles of ammonia, based on my balanced equation, 1 mole of nitrogen for every 2 moles of ammonia, I must have reacted 1.5 moles of nitrogen. And based on the fact I have 3 moles of ammonia, and I know I'm going to get 3 moles of hydrogen for every 2 moles of NH3. So I must have used, this is what we used, I must have used these amounts of the starting material. So now we just look at the question. I know that I use, so I'm going to make this, I'm going to just write a little change here. So I know that I end it with 3. I would have used 1.5 moles of nitrogen, and I would have used 4.5 moles of hydrogen. I would have gained 3 of those. So I know that before and the change needs to equal the after. So I would have had to have 4.5 moles of nitrogen and 7.5 moles of hydrogen. So to clarify that, the start would have been 4.5 moles of N2 and 7.5 moles of H2. So using a little bit of logic and stoichiometry, looking at an equation. So we can go ahead and do that calculation. 30 grams divided by 78 grams per mole gives me 3.846 moles, and then it's 1 mole per 1 mole, so 0.385 moles of the bromobenzene. Br. Now we'll do 65 grams of bromine, Br2, over 1 mole. Each atom of bromine is 79.9 grams per mole, but I have 2 of them, so 159.8. And 1 moles of the bromobenzene for every 1 mole of bromine. 65 divided by 159.8. 65 divided by 159.8 gives me 0.407. So it's pretty obvious what our limiting reactant is. Our limiting reactant is going to be benzene. So if this is my limiting reactant, this is my theoretical yield. So if the actual yield of bromobenzene was 42.3 grams, what was the percent yield? So I'm actually just going to turn the theoretical yield into grams so they're in the same unit. So 0.385 moles. So bromobenzene will be 6 carbons plus 5 hydrogens and plus a single bromine atom at 79.9. So turn it over. Times 0.385. C6H5Br. So this still is my theoretical yield. So now I'm going to do my percent yield. And that's my actual yield, 42.3, over my theoretical yield. Equals 70%. I have 70.03%, but I'll just round it off to 70%. So let's move to our next question, which is formatting on the handout is a little bit weird, but solutions of sulfuric acid and lead acetate react to form solid lead 2 sulfate in a solution of acetic acid. So write the balanced equation. So H2SO4 plus PbCH3COO2 yields PbSO4. Oh, it's 2 and 2, so it's brackets not needed. And acetic acid. So we have an aqueous compound. All acetates are aqueous. Solid. And all acids are aqueous as well. So if 7.50 grams of sulfuric acid and 7.5 grams of lead acetate are mixed, calculate the number of grams of sulfuric acid, lead acetate, lead sulfate, and acetic acid present in the mixture after the reaction. So we're just going to start. We'll set it all up. So I have 7.5 grams of sulfuric acid. And we're going to go to moles. 32 plus 2 is 98 grams per mole. Equals 0.0765 moles of sulfuric acid. Before we go too far, we should make sure we balance. I have 1 sulfate, 6, 7, 8. 2 acetates. I think 2 acetates here. And we're good. 6, 7, 8, 8, 4 carbons, 4 carbons, 1 lead, 1 lead, 1 sulfate, 1 sulfate. Yeah, we're good. We always need to make sure we check our balancing before we go too far. So we'll start with this, and I'm just going to use it to figure out lead sulfate. So lead sulfate is 1 mole. PbSO4, H2SO4, lead sulfate's molar mass is 207.2 for lead, plus 32 grams for sulfur, plus 4 times 16 for oxygen. So 303.2 grams per mole. 0.0765 moles of sulfuric acid times 1/1 times 303.2 is 23.2 grams. So that's how much lead sulfate would be produced if that was the limiting reactant. So I've checked that one. Now I need to move to the lead acetate. So let's give ourselves lots of room here, and we'll do it. I'll try and do it all in one line. So 1 mole of lead acetate is going to be equal to, so we'll just do the acetate by itself. So 2 carbon is 24. Just doing the acetate by itself right now. 3 hydrogens plus 2 oxygens. So 59 grams per acetate. I have 2 of them. And then add in the lead is 325 grams. So I'm in moles, so grams to mole, mole to mole. And now to grams of lead sulfate. So let's roll along here and see what we get. 7.5 grams of lead acetate. So let's go to moles. Times 1/1, and we'll put that in the calculator. Times 303.2 is 6.99 grams. This is far less than that. So this is my limiting reactant, lead acetate, making sulfuric acid my excess reactant. So now that we have lead acetate listed, that's PbSO4, we can start just working our way down on the problem. The problem is kind of a lot because it wants to know how much of everything we have. So I'm just going to make a checklist over here so we don't forget anything. H2SO4, lead acetate, lead sulfate, and acetic acid. A little answer box down here. We'll just keep track of what we have. So lead acetate is a limiting reactant, so by its definition, we will have none of that at the end. And this is all for at the end of the reaction. Because this is the limiting reactant, we did a calculation. We know we're going to have 6.99 grams of lead sulfate. The two things we have to do now is we have to figure out how many grams of acetic acid do we have. So we're basically just going to do a calculation like this again. And then how much is left over from our excess reactant. So let's just do acetic acid first. So 7.50 grams lead acetate. 1 mole is 325 grams. Acetic acid is 2 moles to 1. So we need to make sure we reflect that in our calculation. And then we need the molar mass of acetic acid. So I have 2 carbons, 4 hydrogens, and 2 oxygens. So 7.5 divided by 325 times 2 times 60 equals 2.77 grams of acetic acid. So I'm going to go add that to my little checklist I got going on here. The final thing is my limiting reactant. So I have to do that calculation one more time. 7.50 grams of lead acetate times 1 mole is 325 grams. It's 1 to 1. I should be probably writing out 1 mole of sulfuric acid over 1 mole of lead acetate, but I'm just doing that as we go along. Sulfuric acid, I already did the molar mass of it up here, so it's 98 grams per mole. Let's see what we get. 7.5 divided by 325 times 1 over 1 times 98 is 2.26 grams. And this is the one where it's really important to recognize that that's what we used. So to actually get our calculation, we have to put 7.5 grams of sulfuric acid, take away the 2.6 grams we used. Is 5.24 grams in excess. And there we go, we got everything checked off on our list, and we've answered the question.